This video, we're going to talk about solving a special kind of recurrence relations that fall under the category of linear, homogeneous, constant coefficient recurrence relations of order 2. Now that sounds pretty highfalutin, but essentially what that means is it's a recurrence relation that looks like this. A sub n is d1 a sub n minus 1 plus d2 a sub n minus 2. And the restriction is, since it is constant coefficient, that d1 and d2 are just numbers, element of the reals. Now, these recurrence relations are too complicated to be able to solve by iteration. So instead, we're going to have to solve it some other way. And the way we're going to solve it is by a particular kind of algorithm. Now, what's an algorithm? It's just a recipe, if you will, whereby if you follow it at the very end, you get a solution. Now, we're not going to prove that this algorithm works, but instead what we're going to do is see how to use it. So, here's the way the algorithm goes. Given any recurrence relation of this form, you follow certain steps. First, you solve a quadratic equation, r squared minus d1r minus d2 equals 0. Now, this d1 corresponds to this d1 in the original recurrence relation, and this d2 is that d2 there. And you will notice there's a minus sign here and a minus sign there. Now, whenever you solve a quadratic equation, you're going to get two solutions. And there's going to be two cases. And the two cases are either the roots are different, R1 is different than R2, so you have distinct roots. And our algorithm says that if you have distinct roots to that quadratic equation, then your solution is a sub n is c1 r1 to the n plus c2 r2 to the n. So there's your solution, but what's the problem? The problem is you don't know what c1 and c2 are. How do you determine those? And the answer is by using the initial conditions. Now, the second case, when you solve that quadratic equation, is that you get a repeated root. In other words, both solutions are the same number, R1 and R1. Our algorithm says that if that's the case, you can expect a solution of the form C1 R1 to the n plus C2n R1 to the n. Now, the difference between this equation and this equation, you will notice, is number one, R1 is here and here because I only have one solution to my quadratic equation. And the second term has an n in it. There is no n up there. So again, the algorithm tells us what the solution is going to look like. It's going to look like C1 R1 to the n plus C2 n R1 to the n. But again, we have to determine the constants C1 and C2. How do you determine the C's? Again, it's by the initial conditions. All right, so let's look at a particular example and use this algorithm. The first example we're going to look at is this recurrence relation. A sub n is a sub n minus 1 plus 6 a sub n minus 2. That recurrence relation is good for n element of the set 2, 3, 4, etc. And like any recurrence relation, I have to give you some initial conditions. The initial conditions in this problem are A0 is 7 and A1 is 1. Now, what did our algorithm say? Our algorithm said that we solve a particular quadratic equation, r squared minus r minus 6 equals 0. Okay, where do I get those? Well, this minus 1 comes from the coefficient of a sub n minus 1, which is 1. And this minus 6 comes from the coefficient of a sub n minus 2, which is 6. Now, solving that quadratic equation, we see that it factors into r minus 3 plus r plus 2, which means r is 3 and minus 2. That puts us in case 1 that we have distinct roots. Now, when we have distinct roots, let's go back up here and look. We can expect a solution of this form. So that's what we write. A solution of this form, a sub n is c1 3 to the n. 3 is one of those roots, and c2 times minus 2 to the n minus 2 is the other one of those roots. Now again, all we have to do is find the c's, and we have our solution. How do we find the c's? By using the initial conditions up here. a0 is 7, a1 is 1. So if I take this equation and I plug in n equals 0, I get a0, which I know is 7, but that's got to be equal to what? c1 3 to the 0 plus c2 minus 2 to the 0, plugging in 0 for n. Well, 3 to the 0 and minus 2 to the 0, that's both 1. So I get the equation 7 equals c1 add c2. If I also plug in n equals 1, then I know what? a1 is 1. So a1 is 1. But a1 is also what? c1 3 to the 1, plugging in 1 for n again, and c2 minus 2 to the 1. So that gives me that equation 1 is equal to 3c1 minus c2. All right, so I have two linear equations. One is 7 equals c1 plus c2. The other one is 1 equals 3c1 minus 2c2. And I could solve those by two particular methods that you should recall from algebra, either elimination or substitution. In this case, I'm going to choose to solve it by substitution or by elimination. And to do that, I have to eliminate either C2 or C1. I see the easiest way maybe I could do that is just take that equation, multiply by 2, and I get this. So I get 14 as 2C1 add 2C2. Then I write down the other equation down below there, and I notice this is plus 2C2, this is minus 2C2, so I add those two equations. On the left-hand side, I get 15. On the other side, I get 5c1. That tells me c1 is 3. So now I know that c1 is 3. How do I find c2? Well, easy enough. c1 plus c2 is 7. So 7 is c1 plus c2. C1 is 3, so 7 is 3 plus C2. That leads me to believe that what? C2 has a value of 4. Okay, so if C1 has a value of 3, and C2 has a value of 4, and my solution looks like C1 3 to the n plus C2 minus 2 to the n, then the point is my solution is 3 times 3 to the n plus 4 times minus 2 to the n. Now you will notice that this solution is good for every term, even the initial conditions. So it should work for n element of the set 0, 1, 2, 3, etc., which, by the way, is a set of whole numbers. Now to check to make sure that my arithmetic has been right, my equation then should work at least for the initial conditions. So now I take that equation, I plug in n equals 0 and see what I get. Remember, a sub 0 should be 7. So a sub 0 is 3 times 3 to the 0, plugging in n equals 0 here, plus 4 times minus 2 to the 0. That's 3 plus 4, lo and behold, that's 7. The other initial condition was that a1 has a value of 1. Well, so I take this equation again, I plug in n equals 1. It's equal to 3 times 3 to the 1 plus 4 times minus 2 to the 1. That's 9 minus 8, and lo and behold, 9 minus 8 is 1. So what's the point? I get a nice warm fuzzy feeling. It at least works for the initial conditions. I claim that it's going to work for any term in the sequence. All right, we're going to stop there. In the next video, we're going to do another example, but that example is going to be a little different in that we're going to kick into case 2, where our quadratic equation has a repeated root.